Hello, my name is Mohamed Yusuf, and I'm a data scientist at the Institute of Smart Systems and Artificial Intelligence. Today, we'll cover naive-Bayes classifiers. In machine learning and statistics, Bayesian learning uses Bayes' theorem to update the probability of hypotheses based on evidence and observations. Bayes' theorem was developed by Thomas Bayes, English statistician. Among Bayesian learning methods, naive-Bayes classifiers are a family of probabilistic classifiers which apply Bayes' theorem with strong assumptions. Before diving into Bayes' theorem, let's recap some concepts from probability. Probability quantifies how likely it is for something to happen. Let us consider the experiment of a fair coin toss with a sample space consisting of two possible outcomes, heads and tails. The probability of coin toss event with heads or tails outcome can be denoted as probability of heads equal to probability of tails, which is equal to 0.5. Conditional probability allows us to quantify the outcome of an experiment based on partial information. Here are some examples of conditional probability. In natural language models, we try to predict the next word based on a number of previous words, n-gram language models. In medical diagnostics, we try to predict that a person has a disease given the result of several medical tests. In banking, we try to predict the credit score of a person given the employment status, debts, and the residential status. The conditional probability of event B given A is the probability that the event B will occur given the knowledge that the event A has already occurred. And probability of B given A is equal to probability of A and B divided by probability of A, where probability of A and B, or probability of A intersection B, is the joint probability of events A and B, that is, the probability of events A and B occurring at the same time. The conditional probability can be illustrated using Venn diagrams. Suppose we have two sets of events, A and B, and event A has 4 possible outcomes, and event B has 8 possible outcomes, and their intersection has 2 outcomes. So probability of A will be equal to 4 out of 10, which is 0.4, and the probability of B will be 8 out of 10, and their joint probability, which is probability of A and B, or in other words, their intersection, is 2 out of 10. The probability will be 0.2, and we can calculate the probability of B given A as their joint intersection divided by probability of A, which is equal to 0.5. Now we can derive Bayes' theorem from the concept of conditional probability. How we derive Bayes' rule from conditional probability? Let's write probability of B given A as probability of A and B divided by probability of A. The same way, let's write probability of A given B as probability of A and B divided by probability of B. Combining 1 and 2, we obtain that probability of B given A multiplied by probability of A is equal to probability of A given B multiplied by probability of B. Dividing both sides by probability of A, we obtain Bayes' theorem, which states that probability of B given A is equal to probability of A given B multiplied by probability of B divided by probability of A. Let's explore the terms of Bayes' theorem. Probability of A given B is the probability of event A given that B is already happened and called the posterior probability. Probability of B given A is likelihood. In machine learning, we often want to find the probability of class given the features, which is probability of A given B. Here, we find the likelihood of features B given class A. Probability of A is the class prior probability, our prior knowledge about the class. Probability of B is the feature's prior probability, also called evidence. How do we create machine learning algorithm from this rule? Let's take A as a hypothesis and B as observed evidence, or in machine learning terms, A as a class and B as a features. Let's assume that each sample has n features denoted as x, and we set up our machine learning problem as finding the conditional probability of sample belonging to class C given the probability of its features, and we mathematically denote it as probability of class given features equal to probability of class multiplied by probability of features given class divided by probability of features. In practice, we are interested only in the numerator part, because the denominator doesn't depend on class and the denominator is effectively constant for all different classes. Our numerator is equivalent to joint probability of class and features. Probability of features and class can be rewritten using the chain rule for repeated applications of definition of conditional probability. Firstly, we can exchange the places of classes and features for better representation. Furthermore, using the conditional probability rule, we can rewrite this as probability of x1 given the other features and class multiplied by probability of other features and class. Furthermore, we expand this equation till we got to the point that the last term is probability of xn minus 1 giving the xn n plus. Furthermore, if we naively assume that features are independent, the equation becomes that probability of xi's feature given the other features and class is just equal to probability of xi feature given the class. Now we derive that probability of one feature given the other features and class is equal to probability of this feature given the class. So we know that probability of class given the features is proportional to joint probability of features and class. And knowing this fact, we can rewrite the joint probability as probability of class multiplied by probability of x1 given the class multiplied by probability of x2 given the class, and so on. So the probability of class given the features is equal to probability of this class and the multiplication of all the probabilities of each feature given the class. So we have derived the naive Bayes probability model. If we add some decision rule to the derived probability model, we can construct a classifier. One common rule is to pick hypothesis that is most probable. This method called maximum posteriori, or in short, map decision rule. Bayes classifier is a function that assigns a class label y equal to ck for some k as follows, where we choose the class with highest probability. Now we will see how naive Bayes classifier works in an application. Suppose we want to classify our incoming emails to spam and normal messages. Let's imagine that our inbox had 35 messages consisting of 28 normal and 7 spam emails. We look through all the emails, both spam and normal, and write out all the unique words to create a training set. For simplicity, let's assume that our training set contains 4 words: dear, university, breakfast, and money. First, we create a histogram of all words that occur in normal messages. Basically, histogram is how many times each word was seen. Using the histogram, we can calculate the conditional probability of seeing a word given that it wasn't a normal message. For example, the probability of seeing the word dear in normal message is 40 divided by the total number of messages, which is 40 plus 20 plus 10 plus 5, and will be equal to 40 divided by 75. Similarly, we can calculate the probabilities for other words. The probability of university given that message is normal is 20 divided by 75. Probability of breakfast given that message is normal is 10 divided by 75. And probability of money given normal is 5 divided by 75. The same procedure can be repeated for spam messages. We create a histogram of all unique words that occur in spam messages and then calculate their probabilities. So probability of dear given that spam is equal to 0.22. Probability of university given that spam is equal to 0.11. Probability of breakfast given that spam is 0. Probability of money given that spam is 0.67. Now, imagine we receive a message with the content university dear. We first calculate the probabilities of this message being spam and normal. To calculate probability of this message being normal, we start with the initial guess that it is a normal message, regardless of this message being normal or spam. Probability of this message being normal is equal to number of normal messages divided by total number of messages, which is 28 divided by 35. And the probability of this message being normal, given that its content is university year, is equal to probability of normal multiplied by probability of university given that normal, and the probability of year given that normal. So it is equal to 0.8 multiplied by 0.27 multiplied by 0.53, which is equal to 0.12. We just plugged in the values. We can think of this as a score of message being normal message. Same procedure is repeated for calculating the spam score. We calculate the probability of this message being spam, which is equal to 0.2, and plug in the values, which will be probability of spam given that content is university year is equal to 0.2 multiplied by 0.11 multiplied by 0.22, which is equal to 0.005. So having calculated two scores, we can decide whether this message is spam or normal. We classify the message university year as normal, since it has a higher score being normal message. Now consider the message money, 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 breakfast. Initially, we can guess that it should be classified as spam because it contains the word money 3 times in it, with the probability of money given that spam larger than the probability of money given that normal. But let's do the calculation for both cases. The probability of normal given this message will be equal to 0.8 multiplied by 0.07 multiplied 3 times and multiplied by 0.13, which is equal to 0.0004, which is pretty low score. And as for spam, plugging in the values, we see that it is equal to 0 because probability of breakfast given spam is 0. So this message would be classified as normal message. We get our message money, 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 breakfast, and we classified it to be normal message. But this message contains the word money 3 times in it, and classifying this message as a normal is problematic. The problem arises from the 0 value in the histogram. But this can be solved by adding 1 or any other number to all histogram values. Let's look at the updated histograms with add 1 smoothing. As you can see from the histogram, all the values are increased by 1. And it is the same for spam messages. All the values are increased by 1. And we don't have the 0 value. So that probability of breakfast won't be 0. Having the updated histogram, we should update all the probabilities. So let's update the probabilities. The probability of deer given that normal now will be equal to 41 divided by 79. And the other probabilities will be updated. More interestingly, for the spam messages, the probability of breakfast given Sam now will be equal to 1 divided by 49, which is no longer is 0, and we have 0.02. Let's try to classify the message money, 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 breakfast again with the add 1 smooth naive Bayes classifier. So we have our formula for probability of normal given that message, which will be equal to 0.006 with updated probabilities. Similarly, we can calculate the probability of this message being spam, which is no longer 0. So we can calculate this message as a spam since the probability of spam given this message is larger than the probability of normal given this message. So why naive Bayes is naive? Let's look at our training set one more time. Our training set consisted of words there, university, breakfast, and money. Naive Bayes assumes that existence or absence of one feature is independent to the presence or absence of any other feature. But in real-world problems, the features are usually dependent. We get that the word there is usually followed by one's name. Despite this assumption, naive-Bayes classifiers works very well for many problems. The inference computation is trivial once the probabilities are computed.